Hi, let us quickly go through the summary of Lecture 8. As you already know, we're still discussing the first law of thermodynamics, which basically states that the total energy change of a system is the total energy entering this system minus the total energy that leaves the system. We already seen this multiple times. In this lecture, however, we're going to focus on this left-hand side of this equation. This is what we refer to as the energy transfer. This could happen in three different distinct ways. It could be heat transfer, it could be work that could be done by the system or on the system, and then we have mass flow. We're going to talk about each one of these in detail. So for the first law of thermodynamics, these are some of the notations. We're already aware of this notation, which is concerned with energy. There's another notation that we're going to look at, which is the rate of energy. This is more common in open systems, which have continuous flow. This continuous flow would have continuous flow of energy. Hence, we're going to use different units and a different notation. Now, when it comes to energy transfer, it's very important that we bring up the topic of boundary. Boundary essentially is just a cross-sectional area that we have to define in which we are focusing on, and we look at all the energy that crosses this boundary. This could be the case in a closed system. It could be the case also in an open system. As we said before, the only difference between an open system and a closed system is that open system has mass transfer essentially, which the closed system does not. Right, we're going to begin by investigating closed systems. As we already said, closed systems do not have mass flow, so we're going to talk about heat transfer and work for the energy transfer section in this. We're going to do this in much more detail in the lecture, but let's start with heat transfer. Heat transfer essentially is just the transfer of energy when you have a temperature difference between two separate systems or between a system and a surrounding. So you essentially just have a hotter and a colder region where the heat would just simply flow from the hot to the cold. We're also going to talk about the adiabatic process assumption. This is another assumption like we assumed the ideal gas a few lectures back. This is an assumption that would help us solve a few problems. It essentially assumes no heat transfer. So when you have a perfectly insulated system, you don't have heat transfer between it and its surroundings. That means, in other words, the temperature inside and the temperature outside are essentially the same. We're going to discuss this in more detail and why it's helpful. These are some of the units that we're going to talk about when it comes to energy transfer by both heat and work, and we'll obviously dive into much more detail and use examples. We're also going to talk about a very important notation or convention that we usually go with when we solve problems. This is essentially based on the direction of heat and work. This becomes very, very important, especially when we're solving problems and you have numbers. It becomes easier to write and simplify. Essentially, we know we have work going in and out of the system. We have heat going in and out of the system. So instead, in this lecture, we're going to talk about a way where we define it as signs, so positives or negatives, instead of just writing in and out. We're going to solve a problem using this, and we're going to show you how easy this becomes. After that, we're going to talk about work. We start with the first type of work that we're going to discuss in this course, which is boundary work. When it comes to boundary work, especially in this course, we're going to mainly discuss a piston moving in a system. This could either be a piston compressing the system and going down, or a piston expanding in a system. We're going to discuss how to calculate this boundary work, what it's based on, the theory behind it. We're also going to discuss a new assumption, which is called the quasi-equilibrium process. This basically says that the entire system has a constant characteristic. With that being said, we're going to solve examples of this, and we're going to go into much more detail. It will be a fun class.